Sylvain is our next speaker, and he is an IC3 research engineer. His interests are in distributed systems and cryptographic protocols. So you've got the floor. And I will
Thanks.
give you a 5-minute warning, by the way.
Yeah, sure. So as I understood, we have 1 hour, right?
Yes, you'll be 1 to 2 p.m.
Yeah, all right. So, okay, so thanks everyone. Hi everyone. So Auditee, it's a tool chain to verify Intel SGX remote attestation reports. It's work with Andrew Miller at the Decentralized Systems Lab and the Security and Privacy Research Group at Illinois. It's also work that is sponsored by IC3. Um, okay, so a brief outline of what we're going to cover. So first, motivation, how this work started. Then we'll go over some background, trusted hardware and Intel SGX. Then look a bit about specifically remote attestation. Then reproducible builds, which is really the main topic of this presentation. Tool chains around reproducible builds and Intel building Intel SGX enclaves. Then there will be a tutorial or demo, and I put here freestyle form because I'm, let's say, I hope to get some interaction and questions from the audience, and it will be maybe it's somewhat like organized and not organized. Anyways, I hope it'll be fun. Then we'll conclude with future work and the conclusion. So first, okay, the motivation. How did this work start? So last summer there was this at Illinois. There was a group that started working on an application that has become now the Safer Illinois and Rockwell Privacy Preserving University Health app for contact tracing. The original work was based on this Enigma MPC safe trace, which is in Rust. So, uh, and then the thing is like they needed help to with remote attestation just to get the thing working. And then the next step was also to have reproducible builds. So it will become clearer a bit later when I explain more details for those who don't have the context. Um, so next thing was to look into this because the safe trace, this thing is based on Rust SGX SDK. And there's an open issue still open on reproducible builds. Basically, it's not available. So this was like the main missing block. So here I just show like SGX chip. Okay, you can view the ecosystem like that. Then you need this remote attestation and you need an attestation service. And there's this important building block which could be seen. It's not really necessarily a research problem, but for sure when you get to real deployments, you need to have it. Okay, and I'll explain later why. But that was like the really important missing block, and it led me into what you could call a real rabbit hole, because the Rust SGX SDK depends on this C++ Linux SGX SDK, and they have some kind of reproducible enclave build like Toolchain, but as I'll explain later, it's like really difficult to work with. Also, maybe to step back a little bit, I'm working in an academic context here, like, right? So a lot of people who are actually working on this are not like full-time engineer, but are actually grad students who have like a huge load of other things to do, and they're just helping with these projects. So if something takes lots of time to just set up, to just get started, it's a real problem. So anyways, that's the basis for the work I'm gonna now present. Okay. Um, so brief background. Okay, secure remote computation. So let's step back from trusted hardware and just consider just the problem of running software on a remote untrusted computer, regardless of the technique that is being used. So the goal is to provide integrity and confidentiality. And what does it mean? Is like if someone just sends data to a remote computer to be computed on, you want to make sure that this data is not changed by the computation or by the software that's running, and that its privacy is preserved. Some people like frame this as like you can think of it like you have like data at rest, data in motion, and then data in use. So here what we're considering is like when data is actually being used. Um, and it's apparently a non-solved problem in the general setting. Fully homomorphic encryption can solve the problem, but just for a limited set of computations, and also with performance kind of like drawbacks. So Intel SGX, okay, is like an attempt to solve this problem using trusted hardware. Okay, just a few words about trusted hardware. So the idea, okay, is just to provide a secure container. Another way to think about it is isolated memory on the CPU or encrypted memory. So, but to just think of it like maybe for this presentation, especially people who don't have background with this Intel SGX or trusted hardware, the easiest to think about is just like some black box, okay? Then some remote user just uploads their computation and data into that black box, that secure container. And the trusted hardware then is like guarantees that it's going to protect the confidentiality and the integrity of the data. Now, there's an important thing that is needed. The hardware itself is not enough. There's an attestation protocol that is required to prove to the remote user that the source code that is actually going to run on that remote computer or in that secure container is the expected code. Okay, so that's the kind of like problem here that we have to deal with. Now, okay, very few brief words, and this is like this slide is not very complete, but anyways, about the SGX threat model, but it's important to keep this in mind. So Intel SGX does not consider physical attacks to be part of the threat model. So basically, if someone has access to the physical machine, okay, they could do like chip attacks and whatever. And that's why, for instance, like in the context of things like MEV, there's this concern that the miners, if they have access to their machine, if the incentives are strong enough, they may just break into their hardware. And so this is not something that's considered in the threat model. And it's also was a problem with this proof of elapsed time. There was this consensus protocol that was proposed by Intel, and they kind of like stepped back and realized that, okay, the incentives for the miners are too strong, or the participants, to actually break into their own machine. Now, side channel attacks are also kind of out of the picture in the sense that it's in the responsibility of the developer to handle these, to prevent these attacks or to have mitigations against them. Now, however, that being said, that many mitigations can be done via microcode. So Intel does like patches regularly against major vulnerabilities. So that means you don't have to throw your computer in the trash if there's some major vulnerability that comes out, because most of them are actually fixed via microcode, like firmware updates. Okay, so attestation reports. So how do we want them at a high level? This is like kind of more like the direction that we're trying to go into. So basically here you have an SGX application with some untrusted code and enclave component. And then we want to have some kind of attestation report that tells us, okay, this is a program for this input, and this is like we're claiming that the output is this, and the program that was used like is there available at this sort of public source control, version control repository, like a GitHub or whatever. And then users and public auditors should be able to like use that report attestation, that attestation report, and just to verify it on their own without interacting with the SGX application or ecosystem or Intel or whatnot. Like a brief view of like remote attestation here. Like, okay, so we have this enclave that I referred as like as this black box or this encrypted region of memory on the machine. Then there's this client application. So the blue part here is like untrusted. So basically it could be anything. People who have access to operating system, hypervisor, whatever, is considered to be untrusted. And then this service provider, this is like Intel's terminology, but you could just think of like a normal user, okay, who just wishes to send some data to this enclave and have it computed on in a secure manner. And now this intermediate user, this user here, this client, is going to need to verify with an attestation service whether the enclave is legit, okay? So at a bit of a lower level, what happens is like on the machine, there's this application enclave, which is like secure, like the trusted part. There's applications untrusted. Then there's this quoting enclave. So when there's this challenger, which was this service provider in the previous slide, it requests like to verify that the enclave is secure. or running on legit hardware and so forth. Then the application would like connect this quoting enclave, which is provided by Intel, and the quoting enclave will issue some kind of request to the enclave to produce a report. And the key thing in this report, it'll be this, we'll see this a bit later. There's a special cryptographic hash referred as MR enclave in Intel SGX, which is like kind of, you can think of it as a fingerprint of the source code that is actually has been loaded in that protected region of memory. So that information is returned to the challenger, and then challenger, using some kind of cryptographic protocol named EPID. This, you have to contact Intel here, which a lot of people are not happy with, but this is one way of it. There's other ways to do it, but in this presentation, we're focusing on this approach. I'll talk about the other ways a bit at the end. And then the challenger, like Intel, will just like get back, okay, like this is good or not. And depending on the response, the challenger has to examine the report and then conclude whether they can trust the application or not. And then if they do, then they can start establishing some kind of trusted channel and then send their data for computation. Let's see what I have next. Okay, so where does this Auditee tool that we've been working on comes in is that in that interaction between the challenger and, well, and the application, like I mentioned, this special cryptographic hash, which is like a fingerprint, if you want, or a unique ID for the source code that has been loaded into the enclave. So the trusted hardware guarantees that the source code cannot be changed once loaded into the enclave. However, we want to know, is it the source code that we expect? And the report contains that MR enclave, that cryptographic hash. So the challenger has to check it. But now the question comes like, okay, where do you get that MR enclave? You have to rely on someone to provide you that MR enclave, because what you want to trust in the end, at least that's the position we're taking, is that what you really trust is the source code, not some hash that someone hands you and say, hey, trust this, you know? So, and then in the documentation, it's kind of really hard to understand, because it's like, it's kind of like a bit like considered to be like not a problem. Basically, it's just, yeah, you just check it against the trusted configuration. Or I saw on the mobile coin some issue on their GitHub repo, the golden, they called it the golden validator, will provide you this MR enclave. So it's kind of like really like when someone is just stepping into this and learning, it's like really like mind boggling, like, oh, well, okay, but how do I get this MR enclave? So, and the answer to this is you need to be capable to, Intel calls it a simulated MR enclave. Basically, you using the source code, you can extract, or you build the enclave, and from the binary, you can extract this MR enclave. So we think that is just the most, especially for an auditor, okay, a public auditor, at some point you need to be able to redo these steps. And there's a bunch of other reasons why it can be important to redo these steps. So, okay, on the topic now of reproducible builds. So the problem, okay, so here's some examples, like, for instance, if you look at the, okay, here what I want and what I'm gonna demo, okay, the goal of this whole thing is like, let's say I would challenge you, okay, go to the secret network repository, and because they use Intel SGX, and I just want you to, and let's say you know that they're running some enclaves in production, some nodes, and you have either their binary, you have some remote attestation report that was signed by Intel and so on. And I just want you to check that indeed it's running the code that you think is good. Okay, let's say you're an auditor or you're some super genius. You have scanned their source code, you have a commit hash for this source code. By the way, the cryptographic hash I'm referring that we're calling MR enclave is not the commit hash of a, let's say, Git repository. Okay, it's a different thing. So the challenge here will be, okay, go to either one of these repos like mobile coin or secret network, and just like check that they're running the source code that you think is good. And you'll see that it's not, I tried actually like a few weeks ago, because I thought it would be cool for this presentation to show the usage of the tool I'm gonna demo for these projects, you know, and it's just super non-obvious, okay? And so basically, yeah, how do you build the enclave from source, and how do you verify that a pre-built enclave? Because many of these projects use already built enclaves are assigned by some trusted authority. But here, what we're interested is not trusting the key or someone who's controlling a private key, but we want to trust the source code. So it doesn't matter who signs, okay, in other words. The SGX SDK toolchain for reproducible builds. So as I mentioned at the beginning, like how this work started was that we needed to have, to understand properly how to use remote attestation in the context of this contact tracing project. And because it was using the Rust SGX SDK, which depends on the C++ SGX SDK, we needed to use that to sort of implement or integrate some kind of tool chain that allows us to have reproducible builds. So the C++ SGX SDK is based on something, a tool called Nix and Docker. The problem though is like super cumbersome to use, especially for like, because it's convenient to use. I wouldn't even say it's convenient to use at all, but it's more geared towards like verifying the pre-built binaries that Intel provides. Okay, so such like architectural enclaves, like the quoting enclave, which is provided by Intel. There's this IPP crypto, which is a major dependency of the SDK, and mitigation of been utils and the SDK itself. So it is really oriented towards verifying these binaries that are provided by Intel if you want to check that they really build them from their open source code. But there's no convenient way to integrate that with something like the Rust SGX SDK, and nor with some developer enclaves, okay, in like some kind of like easy to use manner. Okay, so now is the demo. I'm okay even to take questions now if there are any questions. Otherwise, I will switch to the demo. But before, what are we gonna see in that demo? I'm not monitoring the chat, by the way. So maybe Tyler, if you see anything, you can let me know if you don't mind.
Nothing in
So
the chat
we'll
yet.
go over two examples in the demo. One is called SGX hash machine, and the other one SGX IoT gateway. These are toy examples, by the way. And again, think of it like we're in a sort of like academic environment, and it's very useful for, let's say, grad students to just get their sort of like as an entrance, into this topic, and to have some hands-on example to understand the full operation of SGX along with remote attestation and so forth. So, and I didn't mention earlier, but in that, okay, by the way, just as a side note here, so I just in case I'm losing people or whatever. So my goal is that in the demo, we'll go over many, many details where many things will become clearer if it was not clear, like from previous slides. But so in a remote attestation report, there's a special field called report data. And the report data is like user or applications can include their own specific data, and this is 64 bytes. And this can be used, for instance, to put the result of the computation in the report, and then it's verified by Intel and all that, and then you can therefore then trust the result. Another trick is like you put the public key or the hash of the key or hash of data structure. So these are in a way like very, very basic examples in which we show how to do that. And they're like alternative to this official example from Intel, which relies on a shared key via Diffie-Hellman key exchange, which is more involved in some way and more limited, but perhaps has like, it's like a different, it's some different, like if you want trade-offs. So in both example, we'll see like how to generate a quote, sending the quote to Intel for verification, and verifying Intel's response with Auditee, especially checking the MR enclave against some trusted source code. What we can also see, if some of you are interested, and depending on questions, if there are any, how Nix is used to provide reproducible builds, Auditee under the hood, and any questions you have, I'm fine. I'm totally fine to, I don't have a rigid agenda, so I'm okay to derail a bit. And after that, once we're done, we'll come back with more detail on remote attestation in Intel SGX. So let me go to the demo now. Okay, so what I'm gonna first go through, this SGX hash machine demo. So if the screen is not big enough for whatever reason, I will be setting things up just a moment. Okay, so this is just to generate a quote. Okay, so by the way, like, so I'm running this on a computer that has like SGX available, enabled. So now I locally generated this code. You could think of it like I'm the challenger, and I ask an enclave that is deployed. I say, okay, I need a quote. And now the goal of this with this quote is that we send this to Intel for verification. Whoops, I forgot to copy it. So I'm doing certain things manually, and later, if I have enough time, I'll show like how this can be automated. Okay, it's a demo, so things are not well. Just one moment. So if you look carefully in this here, you will see the MR enclave. It's a joke. Okay, why is this like that? Okay, then I won't be long. Okay, so we have a quote. So sorry for this. Now, next thing, we want to send this to Intel. There's like headers that are required. By the way, in order to do this, you need to have like to be registered with Intel service. And when you register, you get this sort of special, you get two things. One is like, you could say is public, which is called SPID. It's like your unique identifier. This is used in their sort of what they call the EPID scheme for verifying the signatures and so forth. And then there's this IS primary key, which is a private API key.
Sylvain, can I interrupt you to ask a question?
Yeah.
So Skyheart in the chat has a pretty solid question, I think. So he asks, or she asks, I'm not sure. Intel's online service is based on EPID, and its unlinkability guarantees provide protection for SGX hardware zero-day exploits. That is my assumption. Once I skip this service and replace it with a more local solution like DCAP, because I do not like the censorship problem of such an online solution, how am I protected from zero-day exploits if only Intel has been made aware of them?
Yeah, it's an excellent question to which I must admit I don't know the answer. It's actually in our like kind of future work, like that we maybe are going to explore DCAP. So we have focused on EPID, the APID scheme strictly up till now. In the context of DCAP, I don't know. I don't know enough. I know there's this project called Opera that is kind of like was built before DCAP was released, and it was kind of concurrent work, but it offers like certain like privacy guarantees that DCAP does not offer. And then in their paper, they mentioned that it's possible to kind of build Opera on top of DCAP, not just on top of the PID scheme. So maybe this can provide some answers, but I would have to look. I don't know, but that could be one pointer. I can later on like post in the Slack channel links to that Opera. It's also in the slides, by the way, which I could post the link to the slide. I'll post the link to the slides in a few minutes. Yeah. Are there any other questions? Or?
Not at this time.
Okay, so I'll keep going, but please feel free to interrupt at any point in time. So, okay, so the response, okay, the JSON response here. So this is now the report we got back, the response we got back from Intel. And what we're really interested, if we get back a response, okay, that means that the hardware is legit. And by the way, in this presentation, I'm really focusing on the MR enclave. There's other things that are important to check, but there I'm considering this kind of secondary in the thing, because without the MR enclaves, it's like again, like it has to match a source code. So that's really the focus here. So what we're interested in is this ISV enclave code body, okay, because this contains the MR enclave. So now I'm going to show briefly how it can be extracted, and later we'll just automate this. Now the MR enclave itself. Okay, so that's the MR enclave we're interested in hexadecimal format. Now I mentioned the report data earlier, and actually in a way I didn't set this example, but so that report data, okay, if some of you have read, I'm gonna jump here a bit, like to step back to just give a bit context that I forgot to give. So this example, okay, that we're going over, the idea, okay, the setup is like that. Just imagine that Elise claims, okay, that the following hexadecimal string is the result of having computed some SHA-256 like 100 million times. Actually, if you try it yourself, if you increase that number a little bit, you'll start to see it takes a long time. But that's not the point. The point, and starting with a hard-coded hello world, okay, string. So the point here is that you could think of it this in a real application. It could be something like, I don't know, like high energy physics calculation or some protein folding thing, whatever you can think of it, that it's take really long time to compute, like maybe months, you know. And then you don't want to have to redo the computation to trust the result. So this example is being used here as a kind of toy for showing this. So basically, this is the source code that you expect to be ran. Like here in our case, it's in C or C++. But the point is like you don't want to have to redo this yourself because it's going to take way too much time. So this is now what we have just done here. Okay, basically, this code. Okay, I did it. I reduced it to just like a million time, I think, because even then it takes a little bit of time. But now this result is the result of having computed the SHA-256 over hello world 1 million times, okay? So because Intel says, yeah, this report is okay, and now we're like, oh, okay, cool. Okay, that means the hardware is legit. And that means, and now if this MR enclave matches the one that you expect, then you say, okay, then I can trust this result. So I don't need to redo the computation myself, okay? So that's really the main goal here. And if I go back to just one moment to just show the thing, let's just do it like for like, okay, we don't, just for the sake of it. Okay, so yes, it does match. Okay, here's like, or if, so you can see that it's like the same thing than the because this thing is 64 bytes. Okay, so this was like a very manual way to do it. Now what I want to show is like if we use this thing Auditee, how what happens with Auditee. Okay. Okay, so how are we gonna do that? So there's different ways now to use Auditee. Let's say there's an interface. No, I'm in the wrong. Sorry, guys. So I'm gonna leave this. Okay. Okay, so let's look at what we have now. Now assume that for what I'm gonna show, okay, we don't need SGX. Let's forget SGX now, it's done. Because I mean, the topic of the talk, right, was something about publicly verifiable reports. Or so let's talk about this now. So let's say you have the response from Intel, whoever provided you. It could have been published on some public ledger, like bulletin board, whatever, Ethereum, whatever you can think of. It's just public. It's made public. Okay, and then you have the headers. You can check the signature of Intel and so forth. Now I want to check if I can trust this. Okay, and the goal is to check this against the actual source code. um, that is claimed to have been running the computation. Okay, so there's different ways to do this with the tool we have developed. One is that so first I have to uh, I want to look. By the way, if it's, I hope it's big enough. So I want to look as, okay, what's the MR enclave that response? Okay, that's in the report, just to very quickly extract that. All right, okay, it's this. And then I want to compare that against, well, let's say, just because this is going to be very quick, let's say I have also a signed binary that I want to check against, that I trust for whatever reason, or I want to be sure, check if this can be trusted, or it can be because I want to deploy it. Or so that's another way to check this. Okay, yes, that seems to match. By the way, the tool can automate this verification, and I'm showing it now manually because it's kind of easier to see. Now the next thing that I really want to check is against the source code. Now we have a way to do this, which is, let's say I trust the source code that is like here. I just take the URL. I can pass a URL or like a local file path. I'll pass the URL here. Now this is going to take a little bit of time because it needs to now rebuild. Now what this is going to do, it's going to build the enclave, sign it with some, the key does not really matter, which it's signed. We need to sign it though, because the way it works. But then once it's signed, then we can use extract the MR enclave out of it. And by the way, under the hood, Auditee just uses like the SGX SDK, especially there's an SGX sign tool that's being used to do that. So now if there's questions, a good time, because it's going to take maybe a minute or two to build. Otherwise, I'm not so sure where to switch to in the meantime, because it's going to maybe too much of context switching. Are there questions? Okay, maybe. Okay, let's talk about Nix then.
Fan has a question.
Yeah, go for it.
Fan says, how do you deal with randomization introduced by the compiler?
Okay, so that was a difficulty in preparing this talk. There's so many facets to this, because I think trusted hardware, Linux SGS itself, it's also a bit like, right? Let's be honest. Okay, some people don't trust it. Some people don't agree about it with it being used. Like in the case of mobile, coin was like obvious, whereas some people say no, it's okay, whatever. So let's forget whatever position one is, but that's by itself, there's lots of stuff to cover there. Now with reproducible builds, it's like a topic on its own, independent of trusted hardware. So, and when I picked this up, when I worked on that, because some people like think, well, actually mobile coin uses Docker, okay, to apparently to reproduce their builds. And I really don't understand how they do it. I've asked a question on their GitHub repo. I haven't gotten an answer yet. But when I looked into that, using Docker was not enough, because Docker can introduce all kinds of like undeterministic issues, because let's say the package manager does not guarantee you which exact version is going to pull. And the solution to fall back to was, I decided to use Nix. This is what Intel SGX also uses for their SDK. And my understanding is the guarantees of reproducibility are like really, really strong. But basically all this to say, I really don't know how to answer Fan's question. I'm sorry, because I didn't go deep enough into Nix itself to see exactly how it works under the hood. I don't know if Fan has something to add to that, or if it makes sense what I said. It's okay if you use a microphone to.
He says that's helpful, thanks.
Okay. Because by the way, most projects really just use Docker for this stuff. It's convenient, but it does not guarantee you. And I can explain later and like show why. But okay, so as you can see, okay, we got the same. So now I'll do a quickly, like an automated way of doing that. So verify. And by the way, we're still working on the interface for this. You know, it's like prototype research, so it's not like polished like software. So I'm passing the source code. Okay, now this is a local path here because I included the signed enclave, and then I'll pass also the report that is already, that you can imagine that, this, by the way, this could be, let's say I'm fetching this from some IPFS, okay? And this could have been provided to me by wherever. It could also be, for instance, I was mentioning one idea for the hackathon, which ended up not being popular, but basically imagine this was like, you can think of Docker Hub, but these like would be a registry of signed enclaves that you can just fetch. And then this is a source code. And by the way, we don't need to verify all three at the same time, but I'm doing it just because it was easier to sort of demo. So now it was very quick because it was already built. But then we have a little reproducibility report here that it says, okay, sign enclave has this hash, bam, bam, bam. And then, yeah, they match. And then the following report data contain remote attestation report, verification report. Then it can be trusted. And here's what it contains. And if you remember when I did the whole thing manually, this corresponded to hashing hello world a million times, okay? So that's it for this hash machine. We have 20 minutes left. So I don't mind to spend more time demoing the other project, which is so I don't, because this is one of the unfortunate thing with this situation is that we're not physically in the same room. So it's hard for me to tell whether there's like no one listening or if there's someone. But the next one, okay, and anyone can interrupt and say, hey, I just want more like sort of just high level concepts. Let's go back to the slides because I have some slides that cover remote attestation, but I'll briefly at least introduce what this thing is. And then after that, we can, see where to go. If some people ask, like, have like preferences. So this is an example based on this gateway, key provisioning, and secure signing using Intel. Okay, by the way, this is something I didn't mention, but this MR enclave is also important when sealing, okay? Because there's this idea of sealing. Basically, you, let's say, create a private key pair. This is what we do in this example. And when you create the key pair, you can seal it and just store it on disk. And because you have this guarantee from the trusted hardware, from the enclave, you have this guarantee that only the enclave code can actually unseal it. And then along when you have this attestation and the verification against the source code using some kind of reproducible build toolchain, then you're convinced that the code is being used properly as expected. And therefore you trust that the enclave will not leak that private key or the secret, okay? And there's two ways to seal. You can seal based on the MR signer, so that means the signature. So in that thing, like here, this enclave sign, so that means whoever signed this. So many applications, it's like kind of simpler. You can say, okay, I trust this developer or I trust this organization. So you can seal based on a public key if you want, or you can seal based on the MR enclave. So it means like whoever changes the code, even if someone you trust, doesn't matter, then you won't be able to seal it if the code has changed, the enclave code, okay? Because the MR enclave will change. So this example, that's what it covers. So this is kind of a simulation, if you want, where a key pair is created, and then it's sealed on disk, and then it simulates to uploading the key, the public key, to the cloud. And this idea, it's like the idea is like for an IoT gateway. That means like you have some sensor data, and you want like the enclave is sitting at the edge of that sensor, and the enclave sort of like signs the data, and you have some kind of guarantee that the data comes from a source that you trust, if you want, okay? So I went over this example and kind of redid it differently such that remote attestation is used, because in that example, there's no remote attestation whatsoever. So I will demo that, okay, now very quickly. And the ID, and I'll explain, it will be easier that I talk meanwhile showing. Okay, so this will be an end-to-end example, actually. Let's do like that. Now, I hope it will work. So if everything works well, there's going to be lots of stuff printed on the screen, and I'll walk back through it as it's like once it's done, maybe, or halfway through. So basically, it creates a key pair, like then and then there's remote attestation. Okay, it's too fast. I had put sleep statements, but it's a bit too fast. But I'll just let it run and then I'll walk back. So okay, here it's stopping. Okay, yeah, I changed my primary key yesterday. Well, I don't know if I will get attacked if you see my primary key. I'll take a chance because it's just a developer, so it'll get you to see a bit more how this thing works. So now this is my outdated key. So this is what I was talking earlier, like, okay, because when a report is generated, it's generated, this SPID is actually an input, okay, to the report, if you want, generation. And it matches. So now, because what happened, okay, and this is I'm requested from Intel, hey, verify this quote. And it says like, nah, it doesn't work because the primary key that I'm using is not the same. It does not match the SPID. So there's lots of like control mechanism here like that. Anyways, okay, I don't want to digress. So okay, sorry, it won't take long. So this is secret. So I will change it after the talk. So okay, it's just an API key. Okay, so I don't know what. Let's rerun the demo. I think I'm not mounting. Hold on, sorry. I'm mounting things. Sorry about that. Okay, apologies. Okay, so okay, just in case it was not clear, right? The goal of this example is that we have some IoT device that is like just producing data, and we have an enclave that is at just like on the edge of it that is like signing that data, and then it's consumed by external parties. And here what we're doing is like there's a key pair that has been generated in the enclave, and the public key is put in the report data of the remote attestation report that is verified by Intel. So any now verifier external remote users can just looking at the report can extract the public key and the MR enclave and check the MR enclave corresponds to the expected source code. And if it does, then they can say, okay, I can trust this public key was generated the way it is generated in the source code. And therefore, like, then it can be used to check signatures. So a lot of applications use this trick, actually. Instead of using the Diffie-Hellman key exchange of this official remote attestation example provided by Intel, this code sample, a lot of applications instead do that. They put a public key or the hash of a public key or of some data structure or certificate. But in the end, it kind of boils down that you have this now key that you can use to verify signatures that are coming out, that are attached to the data is coming out of an enclave. So I hope it works, and if it doesn't, then By the way, I committed tomorrow to do a talk at the RUMP session on trusted hardware. It's called um, Can We Really Hide Atoms? So it will be another side of the picture, actually, just like random thoughts that have been in the background of my, all right, okay, it worked. So now, okay, so now is the thing. So now we have this guarantee that, yeah, okay, it matches. So think of Elise, like check the report, everything. And now she's like, has this data that has been submitted that has been consumed from the sensor. And then she's like, okay, since let's extract this, the public key I was talking about from the report, and let's check it to verify the signature. And then, oh yeah, it was successful. So therefore I can trust this data. That's the idea, okay? And obviously, if some of you are like always thinking, you cannot help to think, yeah, but I have to trust Intel, I have to trust Intel, I cannot. So then attend the RUMP session tomorrow where I will like present my really like just scattered thoughts on the topic. So I think I will stop the demo unless some people are like curious and want to see some low level details. One thing I didn't cover in this, unfortunately, even like an hour goes through quickly for this kind of thing. I'll just show it very quickly. It's like Nix. Okay, yeah, this I want to show very quickly actually. So
You have 10 minutes, so just
yeah, I will be fine actually. So I think this will be interesting. Okay, because I mentioned I kind of complain in a way, say, okay, if you go to mobile coin, the mobile coin, let me go back to my slides actually instead. So I was saying, I kind of like set the problem like, yeah, okay, if you go to this mobile coin repo, let's say, and I want to, I sort of like put this little challenge. Okay, can you check that the MR enclave, like in that report, or they provide, by the way, if you go through their stuff, you'll see that they provide some pre-built binaries you can download and fetch from some uh, registry. Okay, so okay, let's say I just want to check that it matches um, it matches the source code. Okay, that or that some. Okay, so basically what I do, okay, I don't know, there's many ways to do it, but I have included here like a little like Auditee YAML file. Now you can ignore this. So basically here's like where you can just, it's like you can think, some of you are familiar with GitHub continuous integration or like Travis and so on, all this CI infrastructure. So you have something similar like that, that like I'm thinking like that, let's say something like mobile coin would add an .auditee file. Okay. And with this is what Auditee relies on it. It tells you, okay, here's how you build it. You use this default .nix to build the source code, and the enclave file is named this way. So uh, now let's look at the default.nix file, okay? Because this is really what the thing does. Now this is messy, like when looking like that. But basically, Nix has this, like it's this called this derivation. It's basically a functional kind of language to instruct how to build here the enclave from source. Okay, so basically, here I'm kind of like a bit cheating. There's a note explaining why, but anyways, you can also fetch from GitHub. But if so, you could think of it like if it was mobile coin or whatever project, then you will fetch the source code and then you use instruction. Or even better, like I showed previously, there would be this .auditee file that just tells you how to do it, and the Auditee tool reads this and follows instruction to rebuild it. Now there's this important derivation there, which is SGX is used as a dependency. Okay. 5 minutes. Okay, I won't talk about this, but I thought that maybe it can be interesting for you guys to see. So this thing depends on this. So what I would like to see, maybe that's kind of for future work, if like this kind of tool could be integrated such that then just like I was like, that I just demoed, you could just like, you know, you do, okay, hold on, let me do it instead of, uh, so basically here, Sorry, because I cannot. So basically here you would use the tool and you just pass the GitHub repo where the mobile coin is, and it will just tell you what's the MR enclave. Bam, that's it. Okay, or you can do it in a kind of programmatically like I have demoed. So okay, so I'll go back to the slides to sort of close down. So a bit more details about the remote attestation flow. I don't know if it's, yeah, I'll run this very quickly. Um,
5-minute warning.
yeah, I think I will skip this. But basically the main thing here, you have the, okay, just like a few seconds on this. You have this SGX platform. Then you have the Intel services. Here we were focusing on, I didn't mention this provisioning service. I kind of skipped that, but the main thing I was focusing is this attestation service. So when I ran into this problem where my primary key was not working, was not the correct one, it was because of this. And this ISV, you could think of it like any verifier who wants to check, to interact with the enclave. So skip through this. This is a really bad slide, but the thing, it just shows the idea though. There's can be different ways to do this. So when you use this public key trick that I showed in this last example with this IoT gateway, so the host of the enclave could itself say, some people call this like self-attestation, and there was works done like called Decent, where they do that in a more complex protocol. But basically, you just like you request yourself, hey, I need a quote. You send it yourself to IAS with your own account. You get your back the report, and then you publish that report to some public bulletin board, and with the source code that you link to the source code. So in the early slides, that was a bit the idea. Okay. So report data, I will skip this. I'll just go to the end, I think, and take questions if there are any. Contributions and future work. Okay, so there's a next package for the C++ SGX SDK. There's like also for IPP crypto library. Also for these architectural enclaves. There's currently a pull request is open on the Nix packages repository to have the SDK and IPP crypto merge, so it can be much easier to integrate with. There's this toolchain I presented, Auditee, that can be used both programmatically or with a command line interface. Future work in terms of engineering. Okay, we have yet to integrate with the Rust SGX SDK. Use with DCAP, like, so there was a question earlier about that. Used with Opera, integrate with secret network or mobile coin. I don't know if like they would be interested at all, but I'm thinking at least as a proof of concept will be cool. I just didn't have the time to get to it. Then there's a bunch of projects, like research projects like Ikeden, T-Chain, Town Crier, that rely on SGX, that it would be nice to see, to integrate this reproducibility build Toolchain to check the MR enclaves. Then there's these higher level frameworks such as Oclam and Tclave. By the way, all these depends on this Linux C++ SDK. Then I need to improve the packaging of the tool. And then right now it depends. You need to have SGX SDK installed unless you're using the Docker setup. So it would be nice to, I don't know, somehow package it. I don't know. Then research work. I only have one bulletin here, but it's just some thought. So in my work, it just appeared that the reproducible problem is just like it appears it's just treated as an engineering problem, which it may very well be. But I do wonder whether it affects actually real world implementations of protocols, because if you do have a step in the protocol where you need to rebuild to just verify this MR, to extract this MR enclave, it obviously takes time, as you saw. So it would affect the protocol in some way, time-wise, So that's just some thoughts. So, and then we have a bunch of artifacts that are published mainly, I think, all at under the C3 GitHub organization. There's this pull request I mentioned. So big thanks to everyone. IC3, Cornell, UIUC, Intel, Nix Community, Andrew Miller. That's it. And there's a slide with references with papers. For instance, the Oprah paper I was mentioning, it's like, I put it somewhere. I don't know. It's here.
So there's
This
a
is the
couple of
first one,
questions,
actually.
and I think we have time to answer them. We have 1 minute left.
Sure.
So the first question comes from someone named Diliban,
Yeah.
and they ask, what learning resources would you recommend for someone who is keen to get started with SGX?
Yeah, very good question. So this paper, well, it depends what you want to. Okay, so let's split it in two parts: engineering or like hands-on, and theory, like academic. And so this Intel SGX explain, I think it's almost like I think it's the go-to starting point. It's not perfect, but it's really a really really good starting point. Then for things of hands-on, I don't know. I would say like if you use this Auditee thing, not to just kind of like kind of throw myself flowers, but that's kind of one reason for this project is that we wanted to have something easy to use for students where they don't have to struggle just to install SGX, okay? Because it is really not so simple to just like install things. So I would say you can look at Auditee, like go through these examples, run them, and interact, like because you'll have to subscribe to Intel and all that. So that's a starting point. And I think then it depends what you want to focus because there's Intel has all kinds of like facets. There's like the hardware part. Then if you were more at the higher level in terms of remote attestation and so on, then looking there's some links I didn't put here, but there's Usama from I don't know if it's Dresden. I'll put in the Slack. I think he's attending. He has done interesting work on formal verification of remote attestation, both the PID scheme and DCAP. So I think it's very interesting to look at. And yeah, and I would say you can ask people too, because I think a lot of information is scattered and it's not so obvious. And also Intel, uh, I mean, is a company, so it's not necessarily, it's not like documentation. They have a lot of things open source, but certain things are not necessarily easy to start with. Yeah.
Okay, thank you to our speaker.
Thanks, everyone.
Dencrad, are you in the chat? If he has not arrived yet, we do have one more question for you, Sylvain. So I think let's field that while we
Sure,
wait for the
sure.
speaker to show up. So Mohammed asks, why do you plan to use DCAP as well as Opera? They are kind of similar.
No, well, the thing I just saw that. Okay, this paper is like 19. It's 2019, but I somehow didn't see it. It didn't come across my radar or whatever. And I saw just like last week. It's the kind of thing, you're preparing for an exam and you realize that there's a whole section or a chapter in the book that you realize that it's going to be covered in the exam and you never read it. So it kind of a bit freaked me out. So I tried to go over it like as quickly as possible, but and my understanding is a bit like this. It has a lot of overlapping with DCAP, but it has also privacy guarantees that DCAP does not offer. And I don't know the details. I'm not in a position right now to explain why, but this is why I'm interested in looking at both. Yeah.
Okay, thank you.